I'm ready. Yeah.
Hello and welcome to Digital Futures Saturday tutorial series. Today we are pleased to have Runjia Tian covering with us some of the basics of AI and Neural 3D. Before we begin today's session, I would take this opportunity to also introduce our previous series of tutorials which are available in our YouTube library and YouTube archival material. Also today we have, in few hours from now, another of our very interesting Arabic session on space architecture. And next in the series is our tomorrow's session on Sunday headed by Professor Neil Litch, and for FIU DDES program, we will have distinguished guest Benjamin Bratton discussing AI neuroscience architecture, simulation, doubling. Before I begin and give the stage to Runjia, I would just like to very quickly give an introduction to this amazing tutor. Runjia holds a master's in design studies technology degree at Harvard Graduate School of Design. Trained as an architect, he is a multidisciplinary advocate of architecture, computation, and engineering. He investigates the future of design through synergetic engagement of creative computation, extended reality, multimodal media, machine perception, and deep learning. His more recent research focuses on the inactive co-creation between human designers and artificial intelligence. He has also been part of some of the international conferences, including Acadia, ICADI, Cadria, and Neuro IPS workshop. We are delighted to have you, Runjia, here. The screen is all yours.
Thank you for having me for the introduction, and thanks the Digital Future team for this wonderful opportunity to share some of my previous research when I was a student at the GSD about the generative modeling and 3D GAN. So so today will be mainly focused on giving like an overview of the generative 3D modeling and how you can customize your own data set to like a great acquisite data from the website and perform some data wrangling and voxelization on your own. So you can everyone see the screen share now?
Yes, we can. Yeah.
Nice. Okay, cool. Then I just get started. So yeah, a bit of introduction about myself. I came from an architecture background. I did a lot of research at the Harvard GSD regarding the XR and artificial intelligence application in architecture. My master's thesis at the GSD involves using reinforcement learning and parametric modeling for generative modeling of 3D spaces. And currently I'm an interactive engineer at the TikTok effects platform, but today I'm mainly focused on my previous research in architecture and AI. So yeah, and also I started this collaborative initiative called Generative Game for collaborative research in making AI technologies accessible for designers from all backgrounds. So today we'll be mainly going through the basics of using the 3D generative adversarial networks for shape synthesis. And the tutorial will be mainly divided into 3 parts: why we used Voxel for the 3D GAN, and how you can acquire the data for training the 3D GAN and perform some voxelization and pre-processing in your own computer. And the last part will be about neural procedural modeling and how in general, and how 3D GAN can be used for shape synthesis. So we also have a part coming up next month regarding how you can take the results that you get from 3D GAN for some post-processing and visualization in some game engines using the computer graphics, advanced computer graphics techniques, and some shader programming, or some visualization with the physics simulation and real-time engines. So that's it. So yeah, we're gonna first start with a brief introduction about the digital representation of 3D objects. So as architects, like think everyone have the experience of using CAD modeling software for creating their own designs. And there are a lot of like formats, file formats that we deal with when we do the 3D modeling stuff. So reading from the Rhino-Grasshopper's 3DM format, which uses a boundary representation. As you can see, it's a NURB space modeling, and everything is in a curvature status. But there are also other formats out there that exist, like that we don't use a lot in the daily production. For example, like the mesh formats, everything is actually based in mesh, even in Rhino, although it's represented in the BREP format. So what mesh is like maybe the most common like data representation we use in the computer-aided modeling. So it's basically made up of triangle soups, like that compose a 3D model. But mesh is not really a like a really good format for training like shape synthesis networks such as 3D GANs. We're gonna go through why that is the case. So beyond the mesh and NURBS representation, there are also others out there, such as the voxel-based representation, like the famous game like Minecraft, or other like metaverse platforms such as like CryptoVoxel or sandboxes using such representations, where it's easily generalized and it can be applied to multiple scenarios in the like neural networks more easily than mesh. And there are also the point cloud formats where it's used a lot in the geographic data processing. So it's basically you can use a drone to scan some like topographies, and then you get a point cloud file, which is basically composed of various points in the space. So yeah, so you can see we have the different digital representations of the 3D object that we can use. But which one is probably the best for training a neural networks that can, help us synthesize some 3D shapes? Yeah, I think the best answer is the Voxel. So why Voxel is best for training in the generative adversarial networks is because they're actually an extension. You can think them as an extension of the pixel-based and machine learning methods, where it's easily it's kind of like very easy to use the existing technology stack, such as the convolutional kernels in the neural networks to process data and do some like dimension reduction and data compression. Excuse me. Yeah, so using the convolutional kernels in the deep neural networks, you can compress your data information. For example, this is one of the screenshots from the famous 3D GAN paper by Jiajun Wu from MIT in 2016. And as you can see if you read the picture from left to right, so basically it's what the 3D GAN, the generator part, is doing. So it's turning a randomized vector, basically like maybe 1 by 250 to 1 by 200, if I remember correctly. So that's just 200 random vectors. So you upsample the vector into, you convolution the deconvolution the vector into the information, and eventually you get a chair. So so for the generative adversarial networks, you also have a discriminator that compress the 3D data of the chair, 3D information of the chairs into a latent vector Z, like this, if you read the picture from right to left. So yeah, so Voxel, is very in terms of the format, it's very suitable for this scenario, and you can very easily compress the data embedded in your 3D models into some like high-level latent vectors, and like in this case, the latent vector Z. So yeah, that's why it's very easy for us to use the Voxel-based methods to do the 3D like training stuff. And the results are but there are also some like drawbacks of using the Voxel. The main one is that it's very expensive to use, because in a mesh modeling, you always use a shell to represent the solids, But in the voxel setup, and you always you use a solid to represent a solid. So it's not just a shell for the 3D objects, but you also have the opaque flash inside the shell. So that is also, I think that's also maybe you can see that as a disadvantage because it's consume a lot of space to store and compute the resources needed for the voxel models. But it's also, I think, an advantage because you can actually slicing through the model and see what's inside. So it's the actual solid objects if we represent everything in the voxel-based format. And the result using the voxel to train some 3D GANs to extrapolate our existing 3D models is actually very surprising. So as you can see, here is one of the interpolation experiments that the researchers of the 3D GAN presented in their research. So what it is doing is basically turning, it's basically interpolating the two existing shapes. So the first one is the intra-class interpolation, which the researcher takes two voxelized chairs models out of their data set and performing a latent space interpolation between the two different shapes. So this is sharing what we usually call a latent walk in the latent space of GANs. So basically, that's trying to show you the visual interpolation process between two different shapes. So that is, I think, this is a very interesting perspective to uncover some of the the mathematics behind the shapes. How we as humans could probably use that as a way to imagine how two shapes. Is there anything between the two different shapes? So what's more interesting is the interclass interpolation. So as you can see in this example, the researcher interpolates a voxelized car model into a boat model. So yeah, there's something actually in between getting quite interesting. Is that it's like 50% of a car and 50% of that a boat. Yeah, so we can do a lot of maybe somewhere like this. We can do a lot of like this extrapolation or between existing data set to generate new shapes. So I think that is why that is what is really interesting about using the 3D GAN to explore some new possibilities of shape representation and shape synthesis and as designers. Yeah, but and also what another advantage about 3D GAN is that it's quite easy to use. Actually, it's not that hard to aggregate all this data from the from the internet, and you can easily train and do inference on a 3D GAN model on your own. And today we're gonna show you how you can actually train a 3D GAN model that can interpolate your own shapes. So this is one of the experiment I did when I was a master student about how you just generating this latent walk of the different chairs using the 3D GAN model. So yeah, another important thing that we're gonna probably cover in this tutorial is the level of details or the definition of this voxel model that we'll be using for today's workshops. So this is actually regarding the disadvantage of the 3D GAN is that most of the voxel models are very expensive to compute. So for example, if you have first of all, you have to have a dedicated graphics card to be able to run this kind of 3D GAN models if you want to run that locally. Yeah, but the level of details really matters here is that we usually run the 3D GANs in a 64 by 64 by 64 setup. So that is actually quite a low level of details. And if you go one step further to 128 by 128 by 128, you have to have a very, very strong graphics cards. So I was using the NVIDIA 2080 Ti's, and it's still very, you can still only run a small batches of data on that one. But yeah, so that is not satisfactory as a result of today. But I think in the future, when we have more computation powers and the level of details of the 3D GAN models that we synthesize grows, it really began to make a huge difference, as I can see in this GIF that I'm showing, that as you go really high definition of using the even the voxel model is getting really precise result, and it's even more precise than the mesh result because you have the flash inside the model. It's not just a shell model. It's really much very precise. And I think this is maybe the infrastructural step towards the metaverse, that you can represent everything in a same in a uniform format. And what's also good about using the voxel is that there are a lot of data, 3D data in the wild that you can easily translate into the voxel, such as this is one of the examples from the website where one of the researchers from Europe is voxelizing a Lego model. So the model was originally a point cloud that has color. So yeah, and he was using in your case is 256 something definition, and you can get some really decent Minecraft looking data for for training your 3D GAN. So yeah, this means that we can aggregate data from the wild, from the anywhere in the internet, and create our own voxel data set really easily. So about the sources of the models. So first, there's a lot of 3D data set that researchers in the computer science domain have already created or crowdsourced. So for example, the data set that we'll be demonstrating today, which is called ShapeNet, is one of such examples. So in the ShapeNet example, there's a lot the data set that ShapeNet provides is basically like OBJ or OFF models of all of these chairs and of different shapes, and they have thousands of them, so that you can already generate some interesting results out of the experiment, and it's free and open source. And although ShapeNet requires I think it's a verification that you're human, so and then you can download the dataset from their website. I strongly recommend you to look into this data source. It's a huge data repository, about 25 gigabytes of 3D models, and it's very easy to use. And I'm going to show you how this one can be integrated to the 3D GAN workflow as well. But for architecture, we actually didn't have so many 3D model data sets. So I've started this collaborative effort called Generative game to crowdsource the architecture 3D models for the shape synthesis research. So yeah, I'm gonna also post the methods at the end of the tutorial. So if you're interested in joining the crowdsourcing effort of collecting 3D data sets for architecture. Once you have the data set from the somewhere in the internet, the next step is to voxelize them, to turn them into the voxel representations instead of the original OBJ, OFF, or 3DM models. So for this step, we use what is called BeamVox. So it's a free, although not open source, program that developed by the graduate student at Princeton to rasterize a mesh-based or other formats-based, mainly mesh-based models into the into a format called BeamVox. And we're going to use another BeamVox Python library to load this BeamVox into the 3D into our 3D GAN setup. So I'm gonna quickly demo how you can do the voxelization on your own device. And let me just switch the sharing. Yep. So I've switched the sharing to the the folders that are going to be shared, that I think going to be sharing for this tutorial. I think yeah, I think that they have already posted the link to this folder. So I would encourage everyone to maybe, it's easier if you just first download the entire folder and upload that again to your own Google Drive. So it's it'll be much easier or faster in that approach. And yeah, here we're gonna first use this folder called chair. Yeah, if you download that into your personal device, you can see there is first a like executive file called beamvox.exe. So that's what we use for the voxelization process. And there's also these bunches of files called OFF and OFF.annote. The annote is basically what they use for annotation in the in the ShapeNet dataset for other purposes. We do not need to care about these files at all. So what is the chair is actually stored in the OFF data, in the OFF files. And I'm gonna show you quickly how you can easily do the chair interpolations. Do the chair voxelization easily in your on your own device. So let me really quickly change to another screen share. Oh, can everyone see the window now? Yeah. So basically, yeah, if after you download the 3D GAN folder, yeah, you will have this this chair dataset in your own computer. Oh, sorry, just 1 second. I'm putting another location.
Runjia, do you want to give access to the link that you have shared for the drive?
Oh, sorry, I didn't. Oh, sorry.
Yeah.
Let me change.
Yes. Thank you. We'll also share it with our YouTube audience in case everyone's waiting on YouTube.
Yeah. I posted another link to the
yes,
chat.
Thank you. Thank you. Yeah.
Yeah. Okay, so have everyone downloaded the folder already? Yeah, so this part is kind of a little bit tricky to set up in your local computer. So yeah, you download the entire folder into your local device. Yeah.
Also, could you just zoom in to the text? It's a little small. Yeah.
Yeah, sure. I'll start sharing again soon after.
Yes.
Yeah, so can I see the sharing now?
Yes, we can see a lot of
Is
files
it the
in one
folder?
single folder. Yes, yes. We see a lot of MTL files. Is that correct?
Sorry,
You're on mute. Yeah.
Yeah. Sorry, for to use the to use this the bin, to be able to use the Beanbox in your own local device, yeah, it's like you're gonna use the the command line in Windows to achieve that. So basically, what you do is you open either the vanilla Windows command prompt, or if you're familiar with Anaconda, you can also use the Anaconda the Anaconda command prompt to for the processing of this data, and yeah, and after you download the chair folder, I think we already have the beanbox.exe for you inside the. We already have the beanbox.exe for you inside the original folder, and if you can see the beanbox.exe here inside the folder panel, and also there is there is also the chair.off format. So the chair.off is basically the OFF formats of representing the chairs. Let's see. You can, if you have you can import them in Rhino, or you can also use this software called Metlab to to view this kind of like OFF models. So they're nothing but the the mesh representation of all these ShapeNet datasets. And let's go back to this setup. So if you open a command prompt such as, I'm gonna just use the Anaconda in this case. So you first copy the folder inside the folder path inside your address, the address in your computer, in the file manager, and then you go to the command prompt, and you first cd into the directory. So yes, just cd means current directory. So it means that you're doing the file processing on this level of the file. And what we're gonna use is this kind of like magic lines in Windows called so you can just basically paste that into your own command line. I'm gonna post that into the chat and also YouTube channel. So what this does is basically is for the for file is basically looping through the all these files in the current directory, and is finding all the files that is ended with, you can see this .off, that everything ended with OFF will be executed in this command. So what command is going to be executed is cmd cbeanbox c64 and this kind of stuff in the in this kind of like in this sentence. So what this sentence does is that it's basically translating the specific file for into the OFF. Yeah. So what this magic line does is basically transforming all your OFF files into the Beanbox format. Yeah, I'm gonna delete all these Beanbox files in the existing folder. So yeah, we can see how that is. It's just processed one by one. Yeah, I'm just gonna delete all of them. I'm gonna run this again from scratch. Yeah, if you run this command in your command prompt, sorry, there's gonna be a window pop up. I'm not sure whether you can see that on my screen, but yeah, basically there will be a window on the top left corner of your computer, and it will generate all these Beanbox files in your local folders. Yep. So that's how you basically do the voxelization. Unfortunately, we do not yet have a setup for viewing all this Beamworks file. There is one called ViewWorks in their original website. You can Google Beamworks and use that to view your voxel files. But basically, what that does is it's just like a pair of 3D cubes. So yeah, I'm gonna stop this the sharing of this part, and so it's basically if after you finish all your voxelization, you can upload them into the folder in your Google Colab, and I would encourage everyone to upload to the folder called train, so that you have the same directory set up as I do on my Google Drive. So so that you do not need to modify anything in the code just to run it. And after we process the data, the next part comes, the training, how you can use the 3D generated virtual network to synthesize the shapes in the same distribution as the original data set. So I'm gonna not go through too much about the GAN into too much detail. There's a lot of tutorials and lectures are already about generative neural network and deep learning. So I'll just go over like the high-level concept.
Runjia, just sorry to interrupt. Can you just see the chat? We have some issues with the command prompt.
Oh, you cannot see the command prompt, right?
Yes. I think we are facing that issue. Yeah.
Yeah, sure, definitely. Sorry about that.
Yeah, no problem. Sorry to interrupt.
Yeah, so basically, you know how do you open a command prompt in Windows, right? You just click on the Windows button and you type command. You just type command prompt in the Windows, and just in Windows search, and then it should come up. Once it come up, you just type CD and the current folder where you download your chair, the chair folder, and you CD into that chair folder. You just CD and paste whatever you copy from your address panel in the chair folder. And then you CD into that folder. After you CD into that folder, you use this kind of like magic line to translate all the file formats. Translate all the files into the Beamworks format that we're going to use for the 3D GAN training. So what this syntax does is basically looking through all the files in the folder and doing the process for you. And if you run that correctly, you're gonna see all this kind of processing printed out in your command prompt, and also there are going to be a window on your screen showing the voxelization process. And some of the syntax that you can modify in your own setup is the D argument in the quotation mark is the precision you want for your model. You can also make it arbitrarily large. I think this one supports 512 by default. But we're not going to use that. I would strongly encourage everyone to stick with 164 unless you have a really powerful 3090 or professional graphics card to perform the 128 training. And also you can change the OFF command to anything like OBJ. I think it supports OFF and OBJ mostly. And this is how you do the customization of this command. But for today, we're going to be using for today's example, we're going to be using the OFF provided by the ShapeNet for this kind of like processing. So does anyone have any question about the? It's the same in the terminal OS, but you have to have the beamworks.exe in the directory. We already have that for you in the chair folder in the Google Drive. So you do not need to copy that again. But if you're running that on your own device, then you have to copy and paste the beamworks.exe file into your folder. Does anyone have any questions regarding this part? How long does the voxelization take? That's a good question. Yeah, it actually really depends on your graphics card. It shouldn't be so. It shouldn't be so slow if you have a dedicated graphics card and you have a. And we are voxelizing into 64. So yeah, this technique is applicable to any mesh object that is supported by the Beambox. I would suggest like if you download any 3DM files or SketchUp files from somewhere on the website, then you might need a Rhino. You can use Rhino to convert everything into OBJ, right? Once you convert everything into OBJ, um, once you convert everything from in Rhino to OBJ, then you can use Beambox to process. You just need to change the .off in this command into .obj. Yeah, that's how it works for if you're aggregating other formats of data. The files I erased from the folder. Good question. So after you perform the voxelization on your local computer, you're gonna upload that again back into Google Drive. So as you can see here in the Google Drive folder, so let's suppose this is the chair that you download from the 3D GAN like repository, and then you have finished the processing. So I will just upload everything into the train folder inside this one. So this, as you can see here, we already have this today, so you don't need to do that. Yeah, but generally in your own setup, I would suggest you upload the folder to the repository called train, and so that you can have the same setup as me, and then you don't need to change anything in your training Jupyter Lab training session, so that you can still do the training. Training in the same setup. Yeah. Does anyone have any other questions?
There's a question from YouTube. It's in the chat. It says for files is not recognized as an internal or external command.
I think it shouldn't be a problem if you're running Windows system. Yeah, this is only supported. The workflow is currently supported only in Windows. Windows command prompt. For Mac versions, that's actually a good question. We haven't yet invented a way to do that in Mac, but I think the Mac Unix have similar syntax. The Mac have similar syntax. It shouldn't be a big deal if you want to do this kind of like loop through the files and translate everything into the Beambox. Yeah.
I think we have a suggestion from Diego in the chat for Mac.
Yeah. If you have, I'm gonna also look into the Mac issue and post similar command lines. But in Mac, I think the syntax is even easier to use the Beambox in the Mac setup. Yeah. Okay. Shall we just keep going?
Yes, I think we're done with the questions. Yeah.
Nice.
Thank you.
Yeah, let's keep going with the tutorial. I think I'm gonna go through. I'm gonna now go through all the details about training the generative adversarial networks. But basically, what it does is, as you can see from this example, it's called GenLab. It's basically like a really nice visualization tool that you can help you easily understand how GAN works. So basically, it's taking in like a random noise, sometimes usually a normally distributed noise, and the generator turns that into maps these input noises using the upsampling convolutional kernels into some either an image or a 3D object. So as you can see here is the sample that gets generated from the from the generator, and it's trying to optimize the weights in the generator so that the generated results are looks more similar to what is called the real here in this visualization. And after this step, the results between the reals and the generated results will be will be compared. And there will also be a discriminator that tells that kind of like judges whether the result is real or not. And then the discriminator will be updated depending on whether it successfully tell the example is real or not. And the generator will also be like updated depending on the gradients calculated from the generated loss. And when these two reaches equilibrium, this like the generator generates something that look real enough, and the discriminator cannot tell. So that's when you have a converged training of the GANs. Yeah, there are a lot of papers out there about how you can do the GAN trainings better. So it's not guaranteed to converge, and yeah, so it might be sometimes tricky to train the GANs. And I'm gonna not go through all the details about that as well, but yep. Sorry about that. I shared the raw folder again. Let me just paste that again into the chat. Yeah, but generally it's hard to train again, but you can use some techniques such as leaky ReLU or further loss function or other fine-tuned methods to make your GAN training better. But we're actually gonna go through some of the details of how the 3D GAN model is implemented by some researchers, and the model that we're going to be using today.
Sorry, you're on mute, Runjia.
Oh, sorry. Yeah. I'm not gonna go too much through too much of the details about the 3D GAN training, but yeah, you can check out. There's a lot of paper out there about how you can make a GAN training converge easy and all the basic conceptions of generative adversarial network. But what we're gonna do today is we're gonna go through how the 3D GAN model is implemented. Basically, we are using this approach. It's like GitHub repo called Simple PyTorch 3D GAN, implemented by like a computer science researcher. It's a very like easy to use frameworks implemented in PyTorch, and we're gonna make some customizations to that, and so that it can run in other definitions. But we first gonna look into how this one is implemented. So basically, if you open the Collab Notebook, in the second link that I posted, so you can see that there's a lot of the code about how this one is implemented. So the first part is the generator. So yeah, typically in a PyTorch setup, you inherit every class of neural network you customized from the torch.nn.module like a class. So this is a uniform like class that you can use for representing the neural network models. And for the generator, it's basically very simple. Just have a couple of convolutional layers. So the convolutional layers is composed of first some upsampling, like upsampling layers that you can see that is first. The ZDIM is basically what we have as the random vector here. So this one is just two random numbers. You can imagine that it's a random number sequence, and we're gonna use a convolutional layer to change that into a like a 3D voxel. But this voxel is very small, and it gradually gets really large after the last deconvolutional layer. And the last one, the layer 5, is given that it's using a sequential layer to connect the conv transpose 3D layers. and using a sigmoid for computing the sigma as the activation function for the last layer. Yep. So that's basically the generator network. So, and also as it also provides some of the like comments about what each of the layers should look like. So for example, your input vector is 32 by 200, like a random vector, but it's only a linear vector because it only has a so it has a dimension 1. And for the second vector, this actually it should be called tensor because it's no longer a it's the 4-dimensional for each of the data. So it has the dimension 2 in the second layer. So you can print out, you can uncomment those and try to print out them in your in the source code if you find some of the training is not correct, and or if you're interested in how this upsampling process works. So basically, it's upsampling our random vector into a 32 by 32 by 32 like a voxel. Yeah, in my implementation, I changed that into the 64 by 64 by 64 or 128 by 128 by 128. So yeah, we're gonna be using this customized implementation for today's training. So for the discriminator, it's basically doing the inverse of the generator. So it's trying to compress the data into a latent vector. Yep, and so that it can tell whether it's true or false based on the 32 by 32 by 32 voxel input. Yeah, and this is how the actual network is implemented. You can check out more about this neural network stuff on a lot of like the deep learning classes of tutorials. And next part comes the how you actually train the model. So basically, it's just like instantiating the 2 different networks based on your input arguments. You can type in a lot of arguments, such as the model's names, the output directory, or the data directory inside your, inside your, inside your like Google Drive folder or your local computer. And then you, for this one, use a for loop to iterate the training through like the number of epochs you define. So each epoch, especially, you can understand that as one training cycle of your network, and use this one training cycle to improve your network. So if you train that for 200 epochs, it means that your network will be improved, like by that number of times inside your training process. Yeah, here is actually the meat of the code is that you generate a z vector from your arguments based on the like the dimensions you provided in the training setup, and then you calculate the discriminator loss and the generator loss after you feed the generated results into the neural networks, and then you perform a backward function call on the loss. It's basically doing the back propagation of your neural networks based on the loss function. Yep. Yeah, so that's basically how that does. And after you train your neural network, you get some of the like the weights of the training point of the training, and you can load them into the models and perform some inference. What inference means is that you're actually using your model to do this cool latent visualization stuff. So yeah, that's basically, and you use the .eval methods, to implement such evaluation of, to turn on the evaluation mode of the neural network so that the network is running inference in that sense. And you can see that the fake, it means that whatever is get generated from your neural network, the Z is again a random vector, and the GZ means that you use your generator to generate a voxel based on that some random vector. Yeah. What's interesting about this one is that you can use, if you have an interpolated random vector, then you're gonna have an interpolated voxel as well. That is the magic about the 3D GAN. And it's also the most interesting visual characteristic that we're going to be leveraging for generating this latent walk of using 3D-GAN. So yeah, after going through all the this is the basics of the 3D-GAN models, if you don't understand all of these all of these details about the implementation, is absolutely fine. You can just use our 3D-GAN training notebook like end to end without without any barriers. So the next part is what we're going to show is basically how you're going to do the training in the Google Colab. Yeah, let me just share my screen again. You can go, if everyone can go to this one, this is the actual training notebook that we're going to be used for today. It's also inside our Google Drive folder. And, it's inside my other 3D-GAN folder, and it's called 3D-GAN training and inference. So if you open the, if you open the Collab notebook, as you can see, first we have some like installation of the dependencies of the package, and also for this one, for 3D-GAN, because it's very expensive, you have to use turn on the GPU setup in the Google Colab. And I think Collab have some free tiers for everyone to use in the if you're using a Collab GPU. So basically, what you're gonna do is you click on the runtime, the runtime and the setup in the Google Colab, and then you select the hardware accelerator to be the GPU. You don't need to change anything else here. So you just save it, and then you can run the blocks without any barriers. So the first cell of this Google Colab notebook is basically just installing all the dependencies like Wisdom, TensorFlow, X, or Open3D. And after you install all these packages, you basically can start your basically you can mount all your Google Drive into the same repository as these Collab notebook. So basically, what it does is actually a virtual machine running on the Google's cloud computing platform, and you're gonna have the data in the same directory from your Google Drive, like copied to this virtual machine and perform this kind of like training. So after you finish the installation of everything, you can start to mount your folder into this training environment. So please don't modify any of the code here, so that, otherwise it might end up breaking the structure. But what is basically you can do is you can use you can just set up you can mount your Google Drive via this setup, and if I have a pop-up window and let you authorize all of your authorize the mount process, which copies all of your files to the training environment. So what it actually does is you can actually see that in the in here is that it copies your entire drive into the My Drive folder, and inside the My Drive you have the 3D-GAN shared folder. So that's why I suggest everyone upload the 3D-GAN folder directly into your Google Drive instead of using the share link to just copy that into the shared space. So as you can see now, we have the relative files that you can access the chair models or the training data set. You have all your you can upload, if you upload your Beambox file here, then you get everything here inside the mounted space as well. And we also get this folder called SRC, which is the source folder that I have modified the original code into, so that you can do the 3D-GAN training and additional features of visualization more easily using our 3D GAN. Yeah, and once you finish all the mounting, you just run this cell. It's nothing but changing some of the system setup for importing all these libraries. And then you run this library, import everything from the source code or from the other PEEP libraries such as Metaplog lib or PyTorch. And this one should run without any issues. So does anyone have any questions up until now?
No questions here on the chat. Yeah.
Okay, nice. Yep. If everything is running correctly, then we can begin doing some interesting stuff here. So if you run this one, it's actually checking whether you have a GPU backend for your training. Yeah, so if this printout is true, it means that you can keep on training, without any issues. But if not, you have to check whether your runtime is changed to the GPU acceleration. Otherwise, this will not work for the 3D GAN setup. And also, we're gonna perform some plotting of visualization of 3D GAN using this setup. So you're gonna open whatever file you pick from your training set. So I will just randomly select one of the chair beambox, and you can click copy path. You can replace this one, file directory plus whatever train chair. Yep. 0036. Yeah, so actually you can just copy that path and you can just paste the entire line here to plot the voxel. So here now you can actually visualize how our voxel looks like in 3D. It's kind of slow sometimes, just because it's essentially doing the plotting in the backend using the GPU. So yeah, it's a nice chair, right? Like you can see everything is in the voxel representation in this data. Yeah, you can also modify the number just to see what other chairs look like. Yeah. So basically, we're using this plot single voxel function that I've implemented in the utils to visualize each of the individual beambox file using Metaplog. So after, this is also doing a stability check here to see whether your model is correctly oriented. So in some cases, if you're using an OBJ model, say you have a SketchUp downloaded from 3D warehouse, you convert that into OBJ using Rhino, and then you have the OBJ files exported and using a beambox to voxelize the OBJ files. But there is a setup in OBJ export in Rhino that usually the Y direction is in the Z direction of the export setup. So in that case, you might want to do this sanity check here to see if your data is in the correct direction. So if you're using that Rhino default OBJ export, you're gonna have your model oriented towards a different direction. So yes, might be sometimes a problem in your training setup. So once we do the sanity check in the Collab, then we can actually fit our model on the chair dataset. So what this does is basically trying to call the main function in the 3D GAN source folder. And there are some some of the things that you have to fill out in this training setup. So the logs is basically what you it's basically what you call this log file. The epochs is the number of epochs you want to run for the training of 3D GAN. I would like to encourage everyone starting from a small batch set so that it does not fail at the beginning. You can gradually increase that into 16, but do not use 32 for some of the setup. It might be corrupting some of your local GPU. If that batch set is too much, it means that it's processing too many data at the same time. And model save step means that how many steps you want to save your model training, the training checkpoints. The model training checkpoint here is very large. It's like 1 gigabytes for each one. So we do not want to save that every step. I usually do 10 steps, but I think 5 is good. Yeah, you can modify those parameters to do some customization. The model name is you just name it either like I just name it 3D GAN chair 64, and the data directory is in the training folder of here. It's actually the training and chair and slash in this folder. And the kubelet, it means that the voxel definition that you use for your training, this has to be the same as your training data. Otherwise, it will raise an error. And the output directory means that where you want the model checkpoints to be stored during the training process. Yeah. Yeah. Let's just try to run this cell and see if anything happens. As you can see, there's the hyperparameter that are logged from this from the program. It's just basically logging whatever you put into the arguments of this command line, this very long command line. Yeah, and you can see here, it's already doing the training. Yeah. Yeah, so here with some of the after you run this 200 apples, it's gonna give you some very interesting results of the 3D GAN that you can move on to do some of the inferences. Yeah, that's basically how you can use the 3D GAN use the 3D GAN setup for training your own 3D GAN models on your own dataset. Yeah, it's not that it's like everything is just so streamlined in the setup, and you can just use whatever data you want to use and with some interesting 3D GAN results. So we're gonna skip the training process. Yeah, but what you can train that for some time and see whether you have any interesting results from the 3D GAN training. And notably, you can go back to your Google Drive and click into the output folder. You can see the same folder that you here that you name in the Google Collab. So this actually stores your training checkpoints. It have all of these like data called images, logs, and models. So images is basically how it looks for each of the training episode. Yeah, you can see it's still just randomly sampling some uniform sample like voxels from the generator, and it doesn't have any good results. And it doesn't yet have any models because we haven't trained that for 10 steps. I said the apples will be 10, so it will save the model every 10 steps. Yeah, but after the training reached epoch 10, you will have something called here we go. I think actually I should have modified this should have modified that somehow in a better, since this one maybe has some issue that it's saving the fifth training checkpoints here. Yeah, but these are the checkpoints that you get from the the 3D GAN training setup. It's actually the fifth training session. And let's see how that looks in the output image. Yeah, as you can see, it's already began to sample some of the distributions and approximately the shape of the chair. Yeah. Never mind. We're gonna just stop the training here, and we're gonna keep with running the inference in the same Google Collab Notebook. Yep. Let's stop this one. So to run the inference, here is also some of the setup, but you have to replace the pass argument with whatever you have created in your output folder. So we have stored our models inside the output 3D GAN chair 64, And you also have this one. This is the folder with automatically generated from the current timestamp, so that none of the two models are gonna override each other. Yeah, we want to copy the path of the generator file. So we just copy that generator file path, and we paste that into this path argument here in this cell. Yep. So this is the model that we want to write inference on. And you also have this obj path where you want to store the inference model into the obj path into your Google Drive folder. So in our setup, we will export everything in the format of a PLY file. So that is the file that is used to store the point cloud. So everything is like a point inside inside this file, and it's basically the same as similar as the voxelization. In the PLY file, we can represent each point to be a voxel, as long as you have the correct dimension in some other visualization software, such as the Rhino-Grasshopper or Unity. Then you can, visualize your voxel again there, turn the point cloud into a voxel. Yeah. So after we finish the setup of the loading directory of the one of the questions, those Unity geometries can be used in Unity for GH. Definitely, that's why we're going to be showing in our next tutorial how you can visualize the training results in other software to visualize them using some shader techniques or voxel-based simulation. Yep. So once you load your generator successfully, you're gonna print out this network structure here, just for it's like a safety check. You can see each of the layers again here in this one. And furthermore, we're gonna use these two kind of code that I implement myself to render some of the to generate a latent walk using the 3D GAN. So as you can see, we have a similar code structure as we did in the previous generator file, that you use the generator forwards method to pass in a random vector in the dimension of 200 by 1, and then the generator gonna throw out a voxel for you. Yep. And I also implemented plot marching cube mesh function, which is using a marching cube method to turn your 3D voxels into a mesh. Yep. So that you can somehow begin to visualize the chairs in the sense of a mesh. As you can see here, we already have some interesting distribution of a pattern of a chair that has like more of the points on the bottom, while less of the point on the upper parts. Yep. This is very primitive training. It's only running on the next epoch, but once you improve the training numbers, it's gonna get some really interesting results. And we also implemented this serialized PLY files, like function that you can call to render your model results into the PLY file. So this one is called sample T point cloud. So basically that's just gonna output everything into your into the object folder and store whichever PLY file here. As you can see, this is the sample point. Oh yeah, I think the sample point call should be stored somewhere in the it's stored here, as you can see. We may want to change the directory of this one so that it does not need stored in the virtual machine, but stored on the Collab. But this one is just a visualization of how you can have the PLY file here. If you download that into your local device, let me see. And you can open the PLY file actually with the MeshLab or Rhino. Rhino can open this such PLY point clouds. You can see this just a bunch of the points that are rendered stored in this file. But you can reverse engineer them back into voxels based on the dimension of each of the voxel points in Rhino or other softwares. Now let's go back to the inference part. So after we can plot each of the single PLFL using the serialized PLFL function. But what if we want to generate some latent walks that have a smooth interpolation between different shapes that we train using our 3D CAN? So here is I wrote a Python generator called, this generator is not the neural network generator, it's just a Python class called generator. So yeah, this one is the generator helps you generate a 3D latent walk using such 3D CAN output. Yeah, so you can define the number of vectors and number of steps that you want. So for example, if I want 10 vectors and 10 steps, it means like I want 10 different shapes and 10 different interpolated intermediate results, including the endpoint of both shapes. So basically that's like 100 frames of 10 different objects that are interpolated using our 3D CAN methods. So you just call this generate 3D latent walk methods. And it's gonna generate the 3D latent walk for you. Yep, I think I can see here. So everything will be ported back into your Google Drive, into the objects folder. Yep, so that you can have all these different latent PLY files there. Yep. I think that's it. Basically for the, and we can also import export those files into other formats of PLI, such as big little Indian binaries, so that it can be used in Unity. Because Unity, I think there's a library to import PLI file, but it only supports big little Indian binary formats for the PLI file. Once you have all these files into in your folder, these are just interpolated, and you can use a simple for loop to iterate through them to generate these latent walks. Should be very simple. Yep. Okay, so and you can also use customize this Paul Martin Cube function to generate a interpolated video of the 3D latent walk in a similar way that we implement the export the PLF file. It's just instead of like writing to a PLF file, it's serializing everything into a picture for you. And you can also use other post-processing tools to turn them into GIFs or other cool visualizations. Yep, so that's pretty much, I think, all of the part about the basics of the how to use the 3D GAN. And why we are using the voxels for representing the 3D GAN methods. Does anyone have any questions?
I think there are few questions from common questions on whether with this workflow can be used with the Grasshopper. So if you can just check your chat, we do have some questions on if voxel geometries can be used in Unity or Grasshopper for simulating robotic assembly. So do you have any thoughts on that?
Yeah, yeah, it's definitely doable. We can definitely explore it. The reason that we serialize everything into a PLY file is that they're very interoperable, and they can easily be imported into other software such as Rhino or Unity for visualizations. Yeah, in Rhino, you might not be able to do any like physics. Oh yeah, maybe Kangaroo is a good example, but the shaders in Rhino still sucks, right? Like, we're gonna use Rhino for some of the shader toys, but Unity is definitely like a better tool for visualizing everything or doing like a real-time physics. Yeah. Oh, yeah. Good question. I think so. There's a question about how many 3D files we need to use in our database. Yeah, that's a really good question. It's actually regarding how you can train a generative adversarial networks really well. I think at least I would suggest that you have at least like 300 samples to get a decent result. Yeah, so for the chair sample, I used all the chair models in the ShapeNet dataset. And you can apply for the access of ShapeNet dataset and on their website. And the chair itself contains, I think, like around 500 or 600 at least chair models. That's already really a lot of files for the 3D GAN. It should be enough for getting the results that I get from the chair dataset.
Yeah, I think we don't have any more questions. There was definitely a discussion on, is it possible to do the same thing on Grasshopper? I think you touched upon it, and we are good to go for the next part. And if there are any questions from participants, please feel free to unmute yourself. If you would like to switch on your video and ask questions directly, we are okay with that as well.
Yeah. Yeah, I think so. There are some questions regarding whether it's possible to do the voxelization in Grasshopper. Yeah, but yeah, as I think Diego also mentioned in the chat that like there I think there are ways in Grasshopper, but it's kind of like not efficient maybe sometimes, and you have to actually convert everything into a file that is readable by Python, right? So since Beamwork is already there as a as an approach to solve such issues, so yeah, just directly use them. Not sure if there are any libraries in Grasshopper that can be very interoperable to export the file that is readable by Python. So that might be like a more of a tech stack related question, but you can definitely do that. But there you might need some effort to to turn that into a Python readable format. Yeah, but it's definitely doable. I think there are also other voxelization tools that you can use in the web, such as Open3D. Yeah, it might be actually it's different from the Beamworks approach, and it's also Python based. But I think the speed is also some of the concern in this setup. Yeah, the Beamworks is sometimes I think it's fast enough. It's implemented in C++, and it's very fast. All right. Do we have any other questions?
No questions on YouTube or in the chat right now. So if you would like to go ahead, yeah.
Nice. Yeah. So yeah, I think that's pretty much all about today's the basics of 3D GAN training. So yeah, what's coming up next is basically how you can use some of the computer graphics techniques to further visualize your voxel, the voxel that gets generated from your 3D GAN model. So yeah, I think in the next lecture, next tutorial, we're going to be briefly going through the computer graphics pipeline, how you can use faders to, create some customized rendering visualization of the 3D GAN models. Yeah, so this is one of the models of the chair that I rendered in Grasshopper using some of the GHGL shaders. And also we're gonna go through some of the physics simulations that you can use to visualize the 3D GAN voxels. So yeah, it's more of like a post-processing or visualization tutorial of how you can use voxel. There's also an advantage of voxel that you can easily visualize them in the physics engines as particles or as rigid bodies. Yeah, so that's basically it. So I have created this community for crowdsourcing 3D models, so you can stay connected if you're interested in crowdsourcing more architecture models in 3D. So that's it for today's tutorial.
I think we do have some questions. Have we talked about the last part in Notebook 3D GAN export in big or little Indian binaries?
Oh yeah, this part we're gonna cover in the next lecture actually. It's just basically we use that as a. It's like Rhino can open the PLI file in the TXT format without any issue, but Unity does not support that format import. So why we're using that little big Indian binaries is that we have to use that step actual step of conversion to make our model usable in Unity. So we're gonna cover that much that part in the next tutorial. Yeah, but I think before so I think the next part is scheduled for March 19th around that time.
Yes, March 19th. I'll just announce that. And then I think we do have one more question, which is quite interesting, is the texture information lost in the training and inference process? Do you have any thoughts on that?
Yeah, so so currently implementation or a drawback of the Beamwalk is that it doesn't have like a really nice support for the the texture part. So if you really want to use the text, you want to use the texture-based 3D GAN methods, it's better to use Open3D for such for the training, so that it keeps the RGB information for you. But we're gonna not cover that in this part. Yeah, so and that part of the code is still under development. So you have to also make some customization to the existing 3D GAN code base so that it can support the RGB training as well. Yeah.
Yes. I think I'll just share my screen and just announce for the upcoming sessions. Thank you so much, Runjia. I think this was a much needed tutorial, especially because we've been talking about AI basics. Do you mind stopping your share? I'll just share my screen.
Sure.
Okay. Yeah. Thank you. Yes, no problem. Yes, this was a much needed tutorial because we have been kind of concentrating on some of these tools in our previous tutorial session, especially some of our early tutorials on AI basics and VQGAN and Clip with Mayur Mistry and Daniel, and then we had a session on Xcool designs and AI design cloud. And this definitely marks the next level for the tutorial series, where we are now able to do the form searching process, if I may call the process of working with the 3D neural networks. Our upcoming session for today is in just few hours. Next talk on Digital Futures Arabic language series on space architecture. And tomorrow we have another session with Neil Litch and with our distinguished guest, Benjamin Bratton. And the next in the series with Runjia would be on 19th of March on Saturday at the same time. And we will be posting the link soon in our newsletter. And we'll be sending all the participants who have been part of this tutorial the link and registration links to the next session. Hope you guys were able to capture all the information. In case you missed out on the tutorial, would be available online on our YouTube archive under Digital Futures Tutorials. See you all in our next upcoming session. Thank you once again, Runjia. It was a pleasure hosting you today.
Yes, thanks so much for organizing all these amazing events. And I also have been a great audience of the Digital Future as well. And thanks everyone for coming today.
Thank you.
Take care of it.
Yes, bye-bye.